In this slide, the schematic or simply basic production technique is shown to produce ferrimagnetic materials. First of all, magnetic material powder with very small diameter, etc., are produced, and then they are put in a container, a strong container, which can be durable in high pressure and high temperature. Heat is applied, and by pressing, force is applied and the pressure increased in that container, and after some time they are not quite melted, but they are softer than solid form, so they are so-called sintered. This is the key word for the process, materials engineering. Sintering process produces ferrite material in the shape of that container. Usually ferrites are cylindrical, or sometimes they are rectangular, prism structure, etc. And the material is encapsulated in small little powders, and in between the powders the electrical resistivity is so high, so eddy current and hysteresis currents, which can be studied in other slides, will be very limited in that volume. So hysteresis and eddy current losses are minimal for eddy current rather, or compared to the solid structures. So there are some slides presented in the lecture notes of ELE361, slide number 28 of these exercises consist of magnetic circuits with a funny shape. In practical life we don't see these shapes very often, but in order to solve that example, to calculate the magnetic flux density in these air gaps, the gap distance G1 and G2 are known, and in the third branch, where there's no gap, there's a coil with N turns, and current I is passing through that coil. And in order to calculate the inductance of this electrical circuit, magnetic circuit, first you have to draw the model. This model consists of circuit elements modeling the magnetic material. So in all these branches you can model the magnetizing or the magnetic circuit component with a reluctance, with reluctance terms according to the geometry. And the air gaps also behave like a reluctance, so they are modeled with RG1 and RG2. So the complete model, to be solvable in the problem, will consist of some core reluctances depending on the geometry and permeability of the material, and magnetomotive force source. The source is N-turn coil, and when we assume the permeability is very high, the core reluctances will tend to go towards zero. So this is another useful assumption to solve these magnetic circuit problems. So the model will consist of a magnetomotive force source and two air gap reluctance branches. So this is relatively very easy to solve in the problem. Then on the same problem at part B, flux density or B field in the first air gap can be found by drawing accurate model. Okay, so B field in that branch is calculated by finding the flux through it and dividing it to the cross section of the B, of the first gap. And of course, the flux does not travel perfectly, rather there's fringing occurs. So you may make some assumptions about, due to this fringing, the cross-sectional area on the average increases by 10% or whatever. So you can calculate the B field accordingly. In another example, given in number 29 of the slides of your lectures, we do have a toroidal core material and loosely wound coil throughout the material, and this material is given to be a plastic. Although it's not mentioned in the question, plastic is neither ferromagnetic nor ferrimagnetic, so we may assume that actually in real life it's not exactly, but we may assume that its permeability equals to the free space permeability. So this is the same as air core material. And the next thing is, after knowing mu, we should know the mean path length. Mean path length is calculated by taking the average of inner diameter and outer diameter. They are given as 150 millimeters and 200 millimeters respectively. So the average is 175 millimeters. This is the mean radius. So we can calculate the mean path length by calculating the perimeter of this circle. So the philosophy is the same. First we draw a model, then find MMF. MMF is found by using these two parameters. Then H is found by using the path length. Then B is found from H, and we end the problem by introducing the result found as magnetic flux density, or B. The other issue presented in the lecture is electromagnetic stored energy. After dealing with magnetic circuits, we may find the flux, magnetic flux density, or magnetic field intensity, or magnetic motive force, everything. Why are we calculating this? Because we may store electromagnetic energy in that magnetic circuit to transfer energy from input to output. So let's focus on electromagnetic stored energy. In short form, many books and resources, it's called as magnetic stored energy. But since this stored energy is given by means of electric terminals, one also may define this as electromagnetic stored energy as well. Now let's consider the simplest case. Known geometry, small gap, 1 MMF and 1 core reluctance, very simple circuit, 1 source and 1 load kind of circuit. And the material has a nonlinear magnetic characteristics. This characteristics is in the horizontal axis magnetic field intensity. The unit is ampere turns per meter, and it's found by MMF over mean path length. So this H, or the horizontal axis unit H, parameter H, can also be exchanged with input current. Why? Because input current is directly proportional with H. So H equals to this, Ni over Lc. N and Lc are geometrical constants, so H is directly proportional with I. So one might also express the same axis by I. Similarly, vertical axis is magnetic flux density, and its unit is Tesla. And this also, okay, magnetic flux density equals to the magnetic flux over cross-sectional area. This area is again a geometrical constant, or instead of flux we may write flux linkage over n. So we may construct equivalent curve with another axis unit. Okay, this is flux linkage. In parallel, we may also construct or represent the same curve with flux. Okay, so current versus flux is also equivalent to the same curve. So in different resources, we may see so-called BH curves or lambda I curves, and they actually represent the same thing, but with some proportionality constants. So the curve shape does not change, only axis values change. So magnetic stored energy, in order to calculate it, we need those curves. How can we obtain magnetization characteristics of a certain material? There is no direct formula to obtain the curve, so they are nonlinear, they are empirical or practical or experimental things. We have to measure them experimentally. We have to apply some current to induce some magnetic field intensity that induces in the material some flux, and flux density can be calculated. So this is repeated in various points to represent the nonlinear curve. We have to do the experiment for as many numbers or points as possible, so the current is changed gradually, step by step, etc. So first we get some material, then we apply current to a coil to introduce H in the material, then we measure the B field in that material. We cannot go into the crystal between the atoms, that's problematic, but approximately we can insert a little magnetic field sensor in the material, but that has some kind of measurement errors as well. Those we make or design the experiment to minimize them as much as possible. Then we change or increase degrees current to have many points to get the H turns, and B field is measured, so we construct the BH curve. This BH curve can be transformed to flux linkage versus current curve as well. So basically this is our material. We wind some coils, wind a coil with number of turns, with a given number of turns, and we change the current through the coil by a controlled power electronic device. So magnetic flux is created within the material. Of course, this material is not ideal, so we create flux in the air as well. So these are called linkage flux. And we start from zero. As we increase the current, we measure the points, we obtain the BH curves. So in the first part of the experiment, at the initial site, we obtain this red highlighted curve. Okay. At some predetermined maximum value, we stop and we decrease the current. As soon as we decrease current, we reach to a point such that the current is zero, but the magnetic field inside the material is non-zero. So we reach to that point. In order to cancel this magnetic field, we have to apply negative currents, reverse currents, and at some point, at some negative current, negative direction current, we end up having zero magnetic flux density. So we may continue by increasing the current in that direction, negative direction. So we end up the, let's say, negative extreme of the current. And we start to decrease the current in the negative direction. By the way, this is the positive direction of the current, and as you can imagine, this is the negative current direction. So it's completely reverse. Then we come to a point such that the current is zero again, but the magnetic flux density is again non-zero, but almost the same value as the previous so-called residual magnetic field. And again, we can cancel or zero that magnetic flux density by introducing positive current. And as we go on, we end up again positive extreme. And by alternating the current from positive to negative directions, we follow this outer path. Okay? So we cannot reach the origin. This is called hysteresis and effect, and this is called hysteresis characteristics. That means the trajectory does not follow its original or the initial trial. Okay. How can we reach the origin? So in order to obtain H equals to 0, B equals to 0 situation, that's also called demagnetizing. Demagnetization. So magnetic materials follow the hysteresis characteristic. In order to demagnetize material, we apply alternating current to the material, and slowly we decrease the amplitude of the AC current signal to zero, so that hysteresis current gets smaller and ends to the or at the origin. So at that moment, the material is fully demagnetized. It's not magnetic anymore. So ferromagnetic materials, at this point, we just introduce magnetic field and return to zero condition. So magnetic flux density remains. That means we can magnetize a material. We can produce magnets. That's the production technique. Inside the circuit, there is a gap, and we insert a material in here, increase the current, take the material out, and this is becomes our permanent magnet. So permanent magnet production is performed simply with this structure. If we have some material which is magnetic, we can demagnetize it by using this trick, so gradually decreasing the amplitude of our AC current of the material, of the magnetic circuit, which holds that material. So gradually decrease the amplitude. Now we come to the electromagnetic stored energy concept. So if a magnetic material is following a hysteresis characteristics, the area under the nonlinear curve and the vertical axis represents the stored energy within the material. And when we come back in the same cycle of the alternating current, some of its energy is released, but the energy proportional to this area is completely lost within the material, usually as heat, or some part is radiation. So hysteresis is not a so good event happening in ferromagnetic materials, because at each cycle some part of the energy is lost, in the material. So we can classify two types of materials. One ferromagnetic material has very fat hysteresis curve. The other ferromagnetic material, as shown, has very thin hysteresis characteristics. This curve, we have to apply high current to obtain relatively low residual magnetic field. We can produce permanent magnets, but the efficiency is low. But for this material, you can apply current and residual magnetic field is relatively high, so you can create good permanent magnets with this material. The area under the hysteresis curve is large for this material and relatively low for this material. So this ferromagnetic material is, in those senses, very good for us. Low hysteresis loss, high residual magnetic residual B field, so it becomes a good permanent magnet. So we may ask a question. Ferrites do have good low loss characteristics. Yes. So this is like a ferrite material magnets characteristics. This is ordinary iron or very simple solid ferromagnetic material. Ferrites have good low loss characteristics. They are produced by sintering magnetic material powders. Could there be a reason that powder sintering is good in terms of decreasing power loss? You may ask why. Why is powdering and powder sintering creates those efficient low loss magnetic materials? The answer lies within the eddy current loss, because the powder is a limited volume and the current is confined, and I square R loss is small compared to high volume circulating currents. So in real life, ferromagnetic materials are used in transformers or electrical machines or etc., both operating under alternating current excitation, also fluctuating but non-alternating so-called DC machines. So definitely alternating current is always present in everyday electrical machinery examples. In those systems, current or voltage at the terminals are assumed to be very good sinusoids, and the current so we assume the voltage is perfect and the current lags this voltage. This is usually the case in those systems, and this current is, due to nonlinear structure of the magnetic material, is not a perfect sinusoid. So follows some kind of curve like this. And in slide 47, also in the textbooks, the shapes and lagging degrees etc. are quite shown. So this is like a borrowing of the figure from these respective sources, like slide number 47 or the textbook. So when you apply the voltage, external voltage E, you observe or obtain current which is lagging due to inductive structure of the machine and the windings etc., and you will observe similar characteristics like this. There will be a lagging, so the same angle crossing for the current is later than voltage, and this lag depends on the circuit conditions. So that ends the summary of the third lecture in ELE361 Electrical Machinery Fundamentals course. So if you have comments, you may reach comments or questions, you may reach from the email address given in this tutoring film.